Hi. First, I want to thank everyone for braving the smoke and then coming to hear us talk about web-scale data ingestion. So my name is GA, and this is Greg, and we're both engineers on the Big Fast Data team at Iterable. So our team's responsible for designing and building the data infrastructure for the entire company. And we're the team that handles all the scale problems that a lot of you probably have experienced or maybe want to experience. So today I'll start by talking about what Iterable is and the scale of the data that we have, just to set a background. And then I'll talk about the actual problem that this talk tries to address, and then also why we needed to make this change. Then I'll talk about the goals that the new solution needs to meet. And then finally, I'll talk briefly about the tools that we needed to use to help solve these problems. And then I'll hand it over to Greg, who will go over our new architecture, and including Scala code that we wrote. And then we'll finally do a look back and then open it up for questions. But in case time is tight, Greg and I will both be at the Iterable booth outside after lunch. So feel free to come say hi and ask questions. So what is Iterable? We can be described as a customer engagement or marketing growth automation platform. We're a B2B company, and so all of our customers are other consumer companies. And our customers use us to send campaigns to their existing users in hopes that their businesses can grow bigger. A simple example of this can include, hey, you like this artist, and they're coming to where you live in 3 months, so buy tickets. And no business wants their campaigns to be spam. They want to send information that's relevant to each individual recipient of their messages. And you don't want to, so for the above example, you don't want to send that reminder to everybody. You just want to send it to people who are interested in the artist and who live in the area. So Iterable provides an automated way for them to do just that. They can dissect and segment their user base to figure out who to send what content to. Our customers can use us to send campaigns via email, mobile notifications, snail mail, really any medium that they want. And Iterable enables this at incredible scale because we have many customers from a variety of different industries. And all of these businesses have varying numbers of users. So here are 18 of our customers that I actually stole from our sales slide deck. But I did want to use it to give a glimpse at the type of the scale that we deal with on a daily basis. So if we look at just Spotify, they report having 83 million paying customers as of this year. But you can imagine how many actual users that they have in total, including the ones that don't pay. And we don't only have Spotify's data. We have DoorDash, Zillow, Box, SeatGeek, AT&T, all of their marketing user data. So in all, we have over 250 customers, and we primarily hold two types of data. The first one is user profiles, so our customers' information. And then events, which describe the individual actions that affect each user. So did Iterable send them something? Did they make a purchase? Did they subscribe to some list or something? And so the data comes to us at peak rates on the order of tens of thousands per second. And we see this fairly regularly, but it averages to be on the orders of thousands per second. This ends up being over 100 million a day, new documents added. We only see these numbers growing in the future because as our customers grow, they use us to grow, so they will grow, and we're going to acquire more customers. So at the end of the day, all the data lives inside Elasticsearch because we want to use it to allow our customers who are marketers to filter and aggregate and make sense of the data that they have with us. So these numbers I pulled a few weeks ago. We have over 40 terabytes of data, over 60 billion documents, around 2,500 Elasticsearch indices spread across 200 data nodes. So the problem, as you've probably gathered, is that we have a ton of user data coming in. So how do we design our data pipeline to be able to handle the ingest, process the data in the order that we receive them, and then make that data useful to the businesses that sent them? Well, it turns out Iterable has been around for 6 years, so we already had a solution. But it just didn't do everything that we wanted all the time. And the all the time is really important as we scale. So the way this old architecture works, marketers use our API to send us requests for events or user updates. Then we buffer those requests inside RabbitMQ, which, if you're unfamiliar, is a queuing system. And then our ingestion service uses Akka actors, not Akka streams, to pull messages, or sorry, it gets pushed the message off the queue and then index into Elasticsearch. One thing to note that a marketer, when they send in the initial request, they can define a custom trigger event that will happen after the original event is ingested. So then if those exist, we publish them back into RabbitMQ, and then they'll get processed the same way. So what needs to change about this architecture? One of the things we really need to change was RabbitMQ, basically in its entirety, the way we're using it. RabbitMQ right now is a single point of failure. If it dies, we're no longer processing anything until it's brought back up. Under very heavy load, flow control inside RabbitMQ will block new threads from publishing to it. This means we would see severe slowdowns and request timeouts on our API layer. And the RabbitMQ client that we were using also doesn't implement backpressure, and it doesn't slow down when RabbitMQ is overwhelmed like it's supposed to. A lot of things are kept in memory, and this is another reason why RabbitMQ dies. We also have to hard code a high prefetch count inside RabbitMQ to allow for high consumer parallelism. The prefetch count indicates how many messages are pushed to a consumer at a time. But what should really happen is that the consumer should decide how many messages they can handle. If a consumer is overwhelmed, we shouldn't be shoving a ton more work down its throat as it's currently occurring. When we do that, it just makes our problems worse. So with the existing architecture, we can't dynamically change the prefetch count, and it's just hard to control the concurrency of parallelism within our streams. Another point that we really need to rethink was how we were doing batching. In the API layer that I showed earlier, we expose bulk update endpoints, but we don't have any restrictions on the size of a batch or the size of each individual update within the batch. So not only that, but we enqueue batch requests verbatim into RabbitMQ, exactly the way our customers who are marketers set them up. So what we end up seeing is batches that require varying amount of work to process. So our data is not regular at all. And we also suffered from messages getting processed out of order in the specific way we were doing batching. I'll show you an example of that. So imagine that a customer sends us batch A followed by batch B. And they both update the same field subscribed on the document, my document. But batch B is supposed to be processed after batch A. But what happens is that batch A can be consumed by one consumer and batch B by another consumer. So when this happens, we can't guarantee that B will finish after A because we have no idea how long each batch will take to complete. But it's really important that we get the correct information because something else could be keying off of that value to figure out if we should send someone something. And if we screw up the order, you're doing something completely different than what the marketer intended. So something else that we found was really flawed was how we were doing error handling, a little bit ironic. But when a RabbitMQ consumer encounters a recoverable error while processing a message, it just kind of gives up, and then it re-enqueues the entire message back into the queue that it found it from. But there are two problems with this. Remember that a RabbitMQ message could be a batch of requests, but maybe only one request in that batch failed. But when we re-enqueue the entire message, what we're doing is we're retrying all of the requests in the batch. So we're doing, including the successful ones, so we're doing a ton of extra work that we don't need to be doing. And the second problem, similar to the ordering problem from the last slide, we could also lose order guarantees when we do this because now the message that's getting retried is actually being processed after messages that came in after it originally. So what we saw in production were performance metrics that looked like this. It was super spiky. In this graph, even though peak performance is about 50,000 messages per second, due to all these zeros down here, where we're doing zero work, on average, we're only achieving about 1/10 of peak performance. And that's not what we want. Has anyone ever sat in traffic in LA? Yes, I have, and it sucks. But anyways, I found an article that said, a few years ago, the average speed on the 101 on a Wednesday night in rush hour was 19 miles per hour. I don't believe that, actually. I think it's lower. But regardless, the actual speed limit on this highway is 55 miles an hour. And I know that most people drive above the speed limit, but ideally, in a perfect world, there would be no stopping and there would be no stops. There would be just no stop and go traffic, because that's what really kills you, kills your overall speed. Yeah, we want that traffic in our data pipeline. So all of these problems that I mentioned manifest as real world issues that affect real people. Our marketers send us messages that we're sometimes not as reliable in delivering. And engineers like Greg and I get called in the middle of the night with alerts saying, hey, queue is not processing. And it's like, figure out why, but everything's so intertwined that it is really hard to figure out. And it's also really hard to fix, like even if we do have a problem. It's usually just, add more nodes. And we don't want to constantly be doing that. Also, of course, documents are occasionally updated out of order. So this is just a correctness issue that we're not doing the correct thing because people use that data. So given all the problems we've identified, we summarized concretely some of the goals we wanted to achieve in our new pipeline that will ensure faster and more correct processing. If you remember our highway analogy, we want to achieve that constant rate of processing at all times for maximizing throughput. We want our speed limit to be the speed at which Elasticsearch can write, and nothing that comes before it should slow us down. We also need to ensure that API requests always work, that we can always handle our customers' load, no matter how big it is. So we need a queuing system that's distributed and highly available to buffer these requests. We also need to ensure that updates are always performed in the order that we receive them so that the data is correct. And finally, we need to handle errors more effectively in order to achieve all the above goals, but it's important enough that it gets a bullet of its own. So here are some of the tools that we're going to use in our new solution, and some of them will just solve some of our goals right off the bat, but other things require more things. So the first one is Kafka. It's a distributed publish-subscribe system for storing and processing streams of data, and we chose it to replace RabbitMQ. It's highly available, and we should always be able to write to it. This will allow us to handle a spiky load much better. It also lets us define the number of partitions and therefore determine the amount of parallelism that we want so that we can maximize throughput. Another tool that we use is Akka Streams, which provides really nice high-level API to slice and dice our data streams. It allows engineers to compose a graph of many steps that the data flows through. Akka Streams implements reactive streams. You guys are on the reactive room. And this makes sure that backpressure is propagated to the source of the stream. This means that no stage should ever be overwhelmed with more work that it can handle. It gives tools to determine how data should be batched and allows developers to easily determine the amount of parallelism that's needed at each stage in the stream. And as Greg will show later, it's easy for any developer to see exactly what's happening inside the stream at a high level, just by reading the code. And then we also use the Alpaca Kafka connector, which turns messages from Kafka as a source for the Akka Streams to consume from. So, and then I mentioned Elasticsearch a few times. It's a distributed search engine built on top of Lucene. And Iterable uses it for its fast aggregation and querying capabilities so that marketers can tell exactly what's going on with their users and with their events. It supports NoSQL, which works really well for us, and it's actually really important for us because we have no idea what format our customer's data comes in as, and every customer's data is different than another customer. So we don't want to set limitations for what kinds of metrics that they want to track by using us. And now I'll hand it over to Greg, who will go over the new architecture and then show you guys some code.
So thanks, Jay. So now I'm going to go over our new architecture. So here's just a reminder of what the old ingestion architecture looked like. And here's an overview of what our new architecture looks like. So what's different here? Well, first of all, we're using Kafka instead of RabbitMQ. And this really solved our flow control issues with RabbitMQ right off the bat. And then we have an Akka Streams graph that consumes from the Kafka partitions and it will write into Elasticsearch. Unlike our previous architecture, we decided we wanted to debatch all the bulk API requests completely when we published to Kafka. And we want to debatch so the amount of work for each individual message is more constant. And the Kafka client will, when you actually publish to the Kafka client, it will do the batching automatically over the wire. So we'll still get the benefit of batching over the wire, but we'll see each update or event individually in the Kafka topic when we consume from it. And we also use Redis here to deduplicate. This gets us a little bit closer to exactly once, even though Kafka's at least once. if the consumer were to die and we need to restart, or if we retry a publish, we could end up with multiple messages. So we use Redis to check to see if we've seen a message before. So at a high level, our graph is parsing the request, then it will rebatch, then it will index those batches into Elasticsearch, then it will trigger any subsequent actions, which could include things like sending emails and triggering new events, and it commits our Kafka offset. And the backpressure of any stage would propagate and eventually manifest as Kafka lag. So if any of these stages are too slow, we'll just see some lag buildup in Kafka. And so for our partitioning strategy, we wanted to guarantee the updates and events for a single user or process in order. That was a very important goal. So we can do that by partitioning by user ID. This way, updates and events can be processed by the same partition exclusively and by the same stream, and we'd have a single thread that's processing, thread of execution that's processing each partition. And we can add partitions if we want to increase parallelism. This works really well because we have a large number of users, and the events and updates are typically spread out among a lot of users. So we can get a lot of benefits from doing this partitioning strategy, and we still can get in-order updates. So now I'm going to go over sort of a simplified version of the code that we use to implement this logic in Akka Streams. It's pretty easy to understand what's going on once you understand the basic Akka Streams primitives. First, we use the committable partition source from the Alpaca Kafka connector, and that gives us a source of sources, one source per partition. So when Kafka rebalances partitions, those sources will complete on the consumer it's revoking that partition from, and it'll restart on the consumer that it's giving that partition to. And then mapAsync unordered will run all these substreams concurrently, and we just emit an element downstream on the outer graph when each one completes. And this just allows us to track the completion of those substreams. So now I'm going to talk about how we process the stream for each individual partition. So the first step here is to parse and validate the message. The messages will enter that stage as a byte string, and they'll leave as a validated message for the next stage to process. So as you can see, we got some zeros and ones that come in, and then we have this nice, pretty validated document. And here's the code for that stage. You can see it uses mapAsync because the actual logic here would usually involve a fetch and a cache or a Postgres DB that is asynchronous. And the parallelism here, we can really use any parallelism we want because the ordering doesn't really matter here. So next we want to batch these messages for indexing into Elasticsearch. And we use a really nice Akka Streams helper called groupedWithin, which allows us to batch elements based on a batch size and a timeout. So for example, if we set groupedWithin to be size 4 with a timeout of 100 milliseconds, and 6 messages come in as a burst, and we don't see any messages for a few seconds, then we get out a batch of 4, and then the other 2 would go into another batch that would be sent off after 100 milliseconds. And the code for that is pretty simple. And these numbers are things you could tweak depending on what the optimal thing is for your use case. For us, it was around 1,000 or so we wanted to get for efficient indexing into Elasticsearch. And this will emit batches to the next stage. So the next stage is responsible for actually indexing those batches into Elasticsearch. It's really the most interesting part of the processing logic. And there's a couple of things that aren't really shown on the code that I want to go over here. When a batch enters this stage, first we want to check Redis and filter out any already processed messages. As we discussed before, this could be if we had a duplicate published, or we had the consumer restarted in the middle of processing, and we saw messages we didn't commit before. This just makes it less likely that we'll accidentally process the same message twice. Next, we want to merge updates for the same user. And this is sort of an Elasticsearch specific thing. Elasticsearch will perform really badly if we try to update the same user twice in succession. It could take like a couple seconds because it has to do a forced refresh. So we want to avoid that forced refresh. And actually, if we have a bunch of objects for the same user, we merge those together into a single update. And next, we want to bulk index into Elasticsearch and track any of those index messages in our Redis consumed element tracker. And finally, we want to retry if we get any retryable errors. So if we get a 429 from Elasticsearch, meaning basically Elasticsearch is too busy doing other things, if we get a 409, which means there's a conflict, we can retry those and basically retry with a backoff until it succeeds. And finally, we'll emit those index documents to the next stage. So here's how we add that to the stream. All that logic is in this dedupe and index function. It returns a future. And again, we want to do a mapAsync with parallelism 1 so we can maintain the strict ordering here. This is just per partition. So now we want to trigger any changes that would happen as a result of indexing this document. For example, we might want to send an email to the user after they get a sign-up event. So those triggered events, there might be triggered events that would publish back into Kafka for later processing by the ingestion pipeline. And after we've done all this, we want to emit the ending offset of the batch to the next stage. And here's the code for this. And I should also mention that because we've used this Redis tracker to filter out process messages, this is basically at most once, meaning that in rare cases, we might have a failure that would cause us to not send an email. But for our use cases, we decided this is better than if we sent 10 emails accidentally to the same user because we were restarting something. And we'll have ways of tracking when this happens so that we can figure out if we forgot to send messages later in the process. So the last step is pretty simple. We just want to commit that offset in the batch to Kafka, and we emit a done. We also use a retry here because occasionally the Kafka might be down, the Kafka broker might be down for a short period of time, a couple hundred milliseconds, and it might make this fail. So we want to retry so that we actually succeed at this. So there's the code, and under the hood, this will use commit Scala DSL from the Alpaca API, and just a wrapper that wraps it with a retry helper. And again, we want to use a parallelism of 1 because we want to make sure that we commit these offsets exactly in order. And finally, we use a nice helper from Alpaca called draining control, which makes it really easy to shut down the stream. There's an example of this in the Alpaca documentation as well. So we use drain and shutdown on this draining control, and we just need to wait for this future to complete. And that will trigger the completion of this outer source, which will complete the inner subsources, and then those will emit elements downstream. And we know once we've emitted those elements downstream, which are just Akka done elements, we know that the partition sources are all done, and we can safely shut down our application. So error handling was kind of an important thing we had to deal with. So how do we think about that? So in our case, we had a lot of unrecoverable errors because our customers kind of define their own data models. So we might have situations where we didn't do a good job validating that data, or they sent us something that we didn't expect. So for those, we typically just track the errors and we continue the stream. And that made sense for our particular use cases. It might not make sense for everybody's use case. For recoverable errors like conflicts, ES rate limits, some of which I discussed before, Kafka broker failures, we can retry those with an exponential backoff. And there's also a whole class of errors we may not have actually foreseen before. We want to, in that case, we actually just do the default, which is to stop the stream in Akka Streams. And that's because we prefer to err on the side of having somebody manually figure out what the error was and handle it, rather than trying to guess what to do and potentially get things into a state that we didn't expect. And we also use a custom Akka Streams materializer. So if you're not familiar with Akka Streams, the materializer is the component that actually runs your stream. And we add a logging, like basically a log there that logs whatever the error is. And by default, the exception might be swallowed in certain cases. So this is just generally a good idea to make sure that you're tracking all the exceptions that happen, and it's easy to see what's going on. So I tried to summarize our progress in some pictures. So our previous architecture, it worked, but it was kind of like a dumpster fire. Well, the dumpster's happy because it usually worked. But there are a lot of situations where it would just catch on fire and not do what we expected it to do. And I kind of think of our new architecture like ice cream. GA really likes ice cream. And ice cream makes her happy just like the new architecture because she doesn't have to wake up in the middle of the night to deal with things going down. And I think pretty much everybody likes ice cream, right? Unless you're lactose intolerant, I guess. And it just handles scale a lot better. It's a lot easier to maintain, and our customers were much happier with it. And especially Akka Streams just made the process of developing it a lot easier. Yeah, so that's about it. If you have any questions, you can ask them now if there's still some time. But you can also come find us at our booth, at the Iterable booth. Yeah, thanks for listening.